Hello and welcome back. Now what I want to talk to you about today is simulation models. Now most of the times components already have some simulation models. Like for example these two components already come with some stock models that LTspice comes with. But other times you will not have a simulation model, you will have to search for one. Like for example for this vacuum tube. LTspice does not come with any simulation models. The same can be said about lots of other transistors and diodes. You will not always get their models with LTspice, so you'll have to search for some models. Now the question arises, how do you know if the model that you found is any good? I mean, who knows who made it? Maybe it's some weirdo in his basement running a YouTube channel. So what I want to do today is look at some ways to check your simulation models by comparing them to the datasheet. So if you're curious about how to do that and much more, then keep watching. Now before starting, I just want to point out something about components in general. This is the datasheet for the 1N4148 diode made by NXP. And this is the datasheet made for the 1N4148 diode made by Vishay. And this is the datasheet made by Diodes. And this is the datasheet made by Fairchild, who was bought over by onsemi. So to summarize, most common components have multiple manufacturers. And that means that each manufacturer will make a slightly different diode. So each manufacturer will have slightly different values in their datasheet compared to other manufacturers. And this is something important to take into account, since just like datasheets and components, simulation models are made by multiple manufacturers. So let's start off by simulating the 1N4148 made by onsemi that comes with LTspice as a stock simulation model. Now there's two things I want to simulate. First of all, how does the forward voltage behave depending on forward current? Now this is a typical curve for a diode, but onsemi somehow made it in a slightly odd way. This is a more familiar shape that you might be used to. So plotting out the forward current based on the forward voltage. So let's see what happens. So what I did here was create a voltage source that goes from 0 to 2 volts in a 1 second interval and directly drive a diode. Now we can see that the current rises depending on time, but just to make a graph that is much more similar to what we see in the datasheet, we can simply swap out time to our forward voltage, so it's a bit more clear. Also, if we go back a bit to our plots, we will see that these start at around 10 milliamps and at 800 and go from about 0.6 to 1.5 volts. So let's just edit our plots a bit. And if we resize it, it starts to look like something we would find in a datasheet. So if we compare this to the NXP graph and we look at the 25 degrees curve, let's see how accurate it is. So at around 1.2 volts, we should be getting around 350 milliamps. And in our simulation model at exactly 1.2 volts, we are getting almost 600 milliamps. So nowhere near the NXP datasheet. Let's see what the onsemi datasheet tells us. Here at 1.2 volts, we should be getting 400 milliamps. So again, we're not even close. Yeah, let's try something else. Maybe that works better. What I got here is a setup for a different parameter that is found in the datasheet, and that is the reverse voltage behavior. So to see how much current goes reversely through the diode, and at some point it should break down and this current should increase to a very large value. Again, if we look in the onsemi datasheet, we see that at around 100 volts this current should exceed 100 nanoamps, and other than that it should be quite small. So I got here a pulse source going up to 200 volts, since around 100 is the breakdown voltage of this diode, and let's just see what happened here. So we can check the current going through the diode and plot it against the reverse voltage. And again, the curve that we obtained is nowhere near what's in the datasheet. First of all, we're only at around 2 point something nanoamps rather than the 15 that we should be at, and anyway, more than 15. And even at 200 volts, there's almost no current going through the diode. Now, something's wrong. I mean, am I doing this right? Is this model wrong? I mean, I'm using the model that LTspice came with, so... Well, the next thing we can try is actually get the model from the manufacturer. You can simply look for a manufacturer, component name, and add spice, and we can see what they have to offer. So here on onsemi's website we can get the simulation model. We have it for this component, and if you download it, you will end up with this thing. So this is also a simulation model with a bunch of parameters, and let's see how this thing behaves. So we can try to add here the graphs that the new model is making. Maybe there's something wrong with the one that was in LTspice. And with the new model, we see something completely different. So we can see that after 100 volts, current shoots up. So the diode is definitely breaking. So this is a very good sign. And if we only view up until 100 volts, and we can do that. And if we only look at the first 100 volts, we see that the current going through our simulation model that we got from the manufacturer himself is a bit more accurate than the one that LTspice came with. I mean, it's still not perfect. We still got completely different values for the reverse current compared to the datasheet, but at least we can see that it actually breaks down. So you can see that this diode actually breaks when you supply it with more than 100 volts. So let's see how is the forward voltage going. Again, if we go back to the datasheet curve, we can check our 1.2 volt point, which should be at around 400 milliamps, and this time we're getting 378. So we're very, very close to what the datasheet is telling us. So this model is actually a lot better. Now I went out and searched for some more models, and I found this thing. This is a highly complicated model made by NXP. So this model doesn't just contain a diode in it, it also contains a resistor. And they're actually telling us that this is not part of the diode, it's just there to reflect how the diode works in reverse operation mode. So let's see if this thing's any better. So again, the exact same circuit, only this time I'm not using the diode symbol, I made a self-generated symbol just to be quick about it. And here, if we look at how this thing is working, so first of all we can look at the current going through the component, almost the same as the one that we got from the onsemi model. And if we look into the datasheet, at around 1.2 volts we should be getting 350 milliamps. And in our simulation at 1.2 volts we're getting a bit more than that. So forward characteristic is not that good. Let's see how the reverse characteristic looks like. So again, we can see that current jumps up after around 100 volts, so that part's good. And if we just look at the first 100 volts, we see a different curve compared to what we got previously. And if we look into the NXP datasheet, there's not really a reverse current graph to compare to. So we can only presume that this might be good, might not be good, who knows. It's slightly lower than the one we got for the onsemi model, but it's okay. So the moral of this is, if you want to have a good simulation, you're gonna need a good model. So let's try something else. Let's try looking at some transistors this time. So what I got here is the BC81740, and I'm using the stock model that LTspice brought that was made by NXP. So I got the model right here, so it's this long endless line of parameters. So to test it, I want to reproduce one of the curves that is found in the datasheet, something that is highly useful, especially when designing amplifiers. And this is the curve that shows the collector current based on collector emitter voltage at various base currents. So here the plot in the datasheet is made with base currents going from 1.2 up to 12 milliamps in 1.2 milliamp steps. And that's what I got here. So I'm generating the base current with this constant current source and using a step parameter. And then I'm varying the collector emitter voltage with this pulse that goes from 0 to 5 volts in 1 second. So let's see what happens. Well, we get this nice curve, and let's just resize it to make it a bit more similar to the datasheet. And we can see that it's somewhat similar, although not really. So first of all, the shape is not that good. I mean, we can see in the datasheet that we have this nice upward going slope in a logarithmic fashion, whereas in a simulation we just get a straight line. The currents are completely different. So the curve in which we get 12 milliamps, at around 1 volt we should be getting somewhere below 0.8 amps on the collector, whereas here at around 1 volt we're getting 1.3 amps, so the currents are also wrong. So what's going on? Well, to solve this mystery, I tried to get the model from NXP, and I got this monstrosity. This is quite a complicated model. It contains 2 transistors, a resistor and a diode, and by combining all of this you get an improved model for the transistor. So let's just see if it's any good. So again, I generated a standard symbol. I didn't really bother to create a very nice symbol for this. I'm using the same currents, same voltages, and this time if we plot out the collector current, we get nothing. So I remade the symbol a bit. I had a problem with the pins. And now we can see that this seems to be a complete mess. We can't really tell what's the difference between the old and the new. So let's just remove the old traces. And now if we compare the two graphs, so the one we got from the simulation to the one in the datasheet, we see that we're getting much closer slope to the one that is in the datasheet. And if we look at a specific point, again the 1 volt, we should be below 800 milliamps, but in practice we're below 1.1 amp. So it's still not very close, but this can be down to transistor gain variations. So the transistor that was tested here has a different gain compared to the transistor that I'm simulating here. Now, speaking about the gain, I found a very interesting graph in the datasheet, and it's this thing. How does the gain of the transistor vary based on collector current and temperature? And the datasheet is showing us this very interesting graph. So we're having a sort of constant gain up until a point in which it starts to drop. So at high currents we're no longer getting that much gain, and gain is highly dependent on temperature. So we can see that for the same transistor we get either 200, 400 or 600 based on the temperature. So I was curious about how this graph would look in the simulator. So I created this setup. Now it's quite similar to the old one, difference being that I'm varying the base current from 1 microamp to 10 milliamps, and I'm giving a constant voltage to the collector emitter of 1 volt, just like the datasheet is telling us. So this graph was generated for a collector emitter voltage of 1 volt, and I'm stepping the temperature from minus 40.25 to 125 degrees. And I will be simulating both models, so the one that LTspice came with and the one that the manufacturer gave us. So this time I've used a logarithmic graph, so I added the x-axis as the current through the transistor, through the collector, and then set it to logarithmic, going from 100 microamps to about 1 amp. And we can see that the gain drops after a certain point, but it doesn't really vary with temperature. So there's something wrong with this model. I mean, it's sort of accurate, but it's sort of not at the same time. So this model that LTspice comes with doesn't really show temperature dependency of gain. So now let's see the complicated model. Now this time we actually get 3 separate graphs. So we can see that gain varies with temperature. Now if we compare to the datasheet, we don't get the exact values that are found here, but at least it's much closer to the real thing. So gain variation is not that big. Actually, I didn't simulate the right temperature. I should be at minus 55, not minus 40. Maybe that's the problem. So yeah, now it's a bit better, but it's roughly still the same. So we can see that the manufacturer's model is much more accurate than the one that LTspice comes with. Oh boy! So until now, I haven't found a model that actually looks like the datasheet. Next thing I want to look at is a vacuum tube. Now, how close do you think that a model that not the manufacturer but somebody online made is to the actual thing? Let's just find out. And for this vacuum tube, I found a model online. Since there's no real manufacturer of this tube anymore, or at least not one that actually provides a simulation model. So this was done by somebody. And it's a model for the 12AX7 or ECC83 or 6N2P tube. Now, if you know a thing or two about vacuum tubes, you will know that the difference between these three tubes is much bigger than the difference between the 1N4148 diode made by different manufacturers, but that's a different story. So what I will be comparing to is the datasheet made by General Electric for the 12AX7. And I will be looking especially at two things. So there are two very special curves that I want to look at, and I will try to reproduce these. So what I want to do first of all is this average plate characteristic. Basically, this is what the collector emitter voltage graph was for the transistor. So what I got here is the anode current based on anode voltage at various grid voltages. And for that I created this setup here. So I will be stepping the grid voltages in 0.5 volt steps from 0 to minus 5. So I will be going to negative voltages. And I'll be increasing the anode voltage from 0 to 500 in about a second. So let's see what comes out of this. So again, I will be needing to edit a bit this graph to make it look more like the one in the datasheet. So we need to go up to only 3.5 milliamps. What's above that doesn't really matter. And now if we compare the two, we can see that they're really similar. So if we take a random point, let's say what happens at 200, guessing 200 is here, when it meets the minus 1 volt curve, we should be getting 2.1 milliamp. Yeah, something like that. So we're getting this brownish curve hitting 200, and at 200 volts we're getting 2.1 milliamps. So just like the datasheet. Oh, this is a good model. Let's just see. Let's not be too quick about this. Let's see this other curve. So another thing that is commonly found in datasheets is the transfer characteristic of the tube. Basically, what's the current going through the anode at various grid voltages and various anode voltages. So this is somewhat similar to the previous curve, only under a different shape. And for that, I created this setup. So basically, this time I will be varying the grid voltage from 0 to minus 5. So our x-axis will be from 0 to minus 5, the grid voltage. And I will be stepping the anode voltage, so from 50 to 300 in steps of 50, so to get the various curves. And we will be plotting to see the anode current. Now, the simulator goes up to 8 milliamps, but the datasheet only specifies 3.5. Now this is partly because the tube is not really designed to go at very high currents. So if you go at very high anode currents, you end up destroying the vacuum tube. So now let's just see how well the simulation compares to the real thing. And again, let's just take a random point. So let's see, when we got 2 milliamps hitting the 200 volt curve, we should be getting minus 1 point something. Let's just see what our simulation is showing us. So when we got 2 milliamps, we're somewhere around here on our 200 volt curve. We're at 1.05, minus 1.05, which is almost exactly the value we get from the datasheet. So surprisingly, you can get really good models for vacuum tubes. Now this doesn't mean that you can't get bad models for vacuum tubes. And this is the case for all components for which you really care about your simulation results. There's a lot of simulation models out there, and it's quite easy to blame the simulator for when the simulated circuit doesn't really reproduce real life. But the truth is that most of the time it's the models that have the problems, not the simulator. So whenever making a simulation, please be very careful with what models you are using. Make sure that the models actually represent how the component works in real life, or at least how the component works within the parameters in which you're simulating. So maybe you don't really care about some extreme values or destructive modes, you just care about certain ranges. And in those ranges you need to make sure that the model looks just like in the datasheet. Now, of course, the datasheet has much more curves, much more data, and all of these can be reproduced using the simulator. And all in all, that's all from my side. So hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and hope to see you next time. Bye bye.